How do we find all the zeros of a polynomial? We know how to figure out the maximum number of possible, but now we're going to talk about rational versus irrational, and even real versus imaginary. So let's jump into it. The first thing that we're going to talk about is the rational zero theorem, which helps us find all the rational zeros of a polynomial. For this, we're going to need a calculator that has a table feature. All right, so here's how it works. You take all of the factors of the constant term, that's this term right here at the end of the polynomial, and you divide them by all the factors of the leading coefficient, 3. And the most important thing is that we try every combination. So all of the factors of 8 divided by all of the factors of 3. So notice on every single factor, we put plus or minus. And now I'm going to come up with every single combination possible and test it with a calculator. All right, so here I've put the polynomial into my table. I'm going to set this to ask. And then I'm going to try out every single combination I can. So like 1 over 1 is 1. But that gives me negative 18. And I'm only looking for things that give me 0. So 2, negative 2. Negative 2 works. As you can see there, 4 works. Let's try negative 4. Negative 4 does not work. 8. Negative 8. Now I got to try all the numbers over 3. 1/3. Oh, 1/3 works. And here I can stop and I'll show you why. All right, so I got x equals negative 2, 4 1/3. Now why was I able to stop here? Well, because I know that the maximum possible number of zeros is 3. And I found 3 rational zeros. Now I'm going to show you one method for if you don't come up with enough roots, what might provide some more. So we're going to check for repeated roots using synthetic substitution. So let's assume we already went through the whole process, okay? And we came up with x equals 1, negative 2, and negative 1. So this is only 3 roots, and I know I have a possible 4. So what I'm going to do is I can just pick any of these, right, and use synthetic substitution with it. So 1, 1, negative 3, negative 1, 2. Go through the process of synthetic. Okay, now I've got it down to x cubed plus 2x squared minus x minus 2. This is factorable by grouping, but hey, might as well just use another one of my factors. I've got negative 2 sitting there, so I can keep breaking this down. Also, I knew I was going to get a remainder of 0 because these are zeros. All right, so after doing synthetic with negative 2, I got down to 1, 0, negative 1, which is just x squared minus 1. Well, I know x squared minus 1 breaks down to x plus 1, x minus 1. So let's look back at all the factors that we had earlier. This x plus 1, x minus 1 breaks down to x equals negative 1 and 1. Well, I've already used 1 and negative 2, and since 1 came up again, this is a repeated root. So all of the zeros of this polynomial are negative 2, negative 1, and 1 with multiplicity 2. So this gives me 1, 2, 3, 4. My 4 roots. But what if this doesn't even work? Well, if you can't get it down to all rational zeros, you might have some irrational numbers or imaginary, and we can just use the quadratic formula to find the rest of them once we break this down to a quadratic using synthetic division. All right, so here we have, let's assume, again, just to make the note short, that we did all the factors of 46 over all the factors of 1, and so far all we've come up with is x equals 1 and 2. So now we're going to have to do synthetic division twice to get this from an x to the 4th all the way down to an x squared. And it doesn't matter which order you do the numbers in. All right, see, here I've done it with 1, and I've come up with these. I need to do it one more time just so I can get it down to a quadratic. And so I'll use this 2. So I'm going to put the 2 on the outside. I'm just going to act like this is my new synthetic division and go through this. All right, so after synthetic division, I've gotten it down to x squared minus 10x plus 23. Well, there's not even two numbers that multiply to 23. I'm going to have to use the quadratic formula. Yeah, remember this thing? It's used to solve roots of quadratics, so let's do it. X equals the opposite of b, so positive 10 plus or minus the square root of b squared would be 100 minus 4 times a times c all over 2a. All right, 4 times 23 is 92, so that's 10 plus or minus 100 minus 92 is square root of 8 over 2, which is 10 plus or minus 2 root 2 over 2. Breaking it all down, that would be 5 plus or minus square root of 2. It's time to bring it all together. The final zeros of this function are x equals 1 and 2 from earlier, and then 5 plus or minus the square root of 2. That gives me 1, 2, 5 plus square root of 2, 5 minus, that's 3 and 4. I've got all 4 zeros of this polynomial. All right, what if I wanted to list those things as a product of linear factors, which is pretty much like, list them out. If they were multiplied, they'd give me back the polynomial. Well, we should know how to do this. If the 0 is 1, then we have a factor of x minus 1. Here we have x minus 2. These get a little bit tricky. This is x minus 5 plus the square root of 2, and x minus 5 minus the square root of 2, which those just change signs. So it's x minus 1, x minus 2, x minus 5 minus square root of 2, and x minus 5 plus the square root of 2, once you distribute this negative to each thing. So this would be the factored form of the polynomial that we just saw. A little challenge is, how would you write x squared plus 1 as a product of linear factors? Well, in this case, it kind of helps just to solve. If x squared equals negative 1, then x equals plus or minus the square root of negative 1, or I. So I could write this as a product of linear factors, x plus I and x minus I. And see, these are linear factors because they're just x's, not x squareds. Let's move on to Descartes' rule of signs. This dude is cool. He's responsible for the x and y coordinate system. All right, the number of positive real zeros is equal to the variations in sign, so positive, negative, of f of x, or less than that number in multiples of 2. So if you had 5 changes in signs, it could be 5, 3, or 1. Okay, the number of negative real zeros is equal to the variations in sign of f of negative x, or less than that number in multiples of 2. So again, like if you had 4 variations in sign, it would be, there's 4 possible negative real zeros, 2, or 0. All right, so we're going to describe the possible real zeros of this polynomial. So for the positive, all I have to look for is when did it change from negative to positive. Well, here we have negative to positive, and then positive to negative. So the sign changed twice. And you can see that this stayed negative. So the number of positive possible real zeros are 2 or 0, because you subtract 2, positive real zeros. For the negative, I'm going to have to look at f of negative x. So I'm going to replace all of the x's with negative x's, and this is going to give me 3x cubed plus 2x squared plus x minus 1. So here we have positive to positive to positive, right? And then we have one change, positive to negative. So the number of possible negative real zeros is 1 possible negative 0. All right, and that's going to wrap up these notes. Goodbye. Bye.